Hello everyone and welcome back to another video that is being recorded because AP weeks are now behind us and I only have two finals to study for, meaning that I'm getting my priorities back in line and doing some ginger math. But what we have here today is zeta of 2n, which essentially is zeta of all even numbers, since n is going to be a natural number. And we're just going to be evaluating this today and putting it in terms of, well, pi amongst other things. So let's get started, shall we? The approach we're going to use in this video does actually rely on some complex analysis. And as such, I'm going to convert the series, instead of being from k equals 1 to infinity, just from being from negative infinity. So we're starting from k equals negative infinity to infinity. And the reason we can do this is because k is actually an even function. So it's going to be symmetrical about 0, meaning that if we sum it from negative infinity to infinity, excluding 0 of course, we just half the value and we're going to get the value of our original series. And as such, we can evaluate this right here rather, well, I say easily, but it's certainly not as complex as some of the other videos I've done in this video on this channel. So what we're going to do is this series right here is going to be equal to, and I'm actually not going to, actually, I'll write out the general formula first. I think that would be more insightful. So in general, if you have a sum from k equals negative infinity to infinity of some f of k, this right here is just equal to the negative sum of the residues of pi f of k, or z really, sorry, f of z, times cotangent of pi z. This would actually be a fun proof to do on the channel. I might do that at some point. But anyway, this is the general formula essentially. So the moment we apply this formula to our 1 over k to the 2n, what we end up finding is that, well, our sum is just going to be equal to the negative sum of the residues. But we're only going to have one residue. And sorry, I should clarify, these are residues at f, residues from f of k, or f of z. But our only residue is actually going to be at 0, because, well, I mean, that's the only place where that can possibly be 0 is 0. So what we have actually is just plugging in our, plugging everything in. We end up finding that we can find the residue of pi times the cotangent of pi z over k, or sorry, z to the 2n, and just at 0. And we kind of have two ways we can do this. You can do it the really nasty way with a bunch of differentiation that takes forever, that I've tried, and it's just really annoying because you have to do like L'Hopital's rule after. It's just, it's terrible. Or we can rely on kind of a different way to look at the residue, and that namely is the fact that a residue at some point is actually just equal to a negative 1, where this a negative 1 term is just the term in front of the 1 over x term in the Laurent series expansion. I hope I'm saying that right. It's French, so I never know. Sorry. I don't know if I actually have any French viewers, but anyway. But in a Laurent series, essentially what it is it's essentially this right here. A1 of it's an extension of a Taylor series of a function, but around it's one of its asymptotes, I believe, or poles. Pardon me. That should not be an x. Plus a2, and all these x's are going to actually be like x minus wherever your point's around. But since our point's around 0, I'm just omitting that. But essentially, this is what a Laurent series is, and you just keep kind of going on here, and then a negative 2 over x squared. This is your Laurent series right here, or Laurent series. And again, this term right here, a negative 1, that right there is just going to be equal to our residue. I'm not going to prove that. Perhaps I'll leave a link in the description of a proof. But anyway, yes. So all we have to do is actually find the Laurent series for that function right here, which boils down to actually just finding the Laurent series for cotangent. which you can conveniently actually just kind of Google, meaning that our residue is just going to be equal to pi times the sum from k equals 0 to infinity of -1 to the k times 2 to the 2k times the 2kth Bernoulli number. I don't know if I'm saying that right or not. Divided by 2k factorial, and then times x to the 2k minus 1, and then all this is going to be over x to the 2n as well. And what we have to find here essentially is this term right here, this a -1 term. And the way we can do that is just, well, we just need to find when this x right here is a 1 over x, meaning that the only power of x we care about in this entire series is actually this x to the -1 term. Meaning we can actually kind of quote-unquote solve for n and k in a way. Or solve for k, sorry. And the reason I say that is essentially because what we can do is we can group our x's together, meaning that we want this x to the -1 to be equal to our x to our 2k minus 1 minus 2n. But what this implies is that 2k minus 2n is just equal to 0. So if 2k minus 2n is equal to 0, then n must be equal to k. Now, heuristically, this might seem a little suspect, but it actually does make sense because it does make sense because if we kind of scroll up here, you'll notice that we said n was a natural number. So it does make sense for n to be k, any whole number from 0 to infinity. So as such, we can essentially eliminate every single term in our summation right here just by replacing, or every term except for the one we care about in the summation, by replacing n with k. And perhaps that wasn't clear. Essentially what we're going to do is drop the summation and replace k with an n. So this right here is going to be equal to pi over 2n factorial times -1 to the n times 2 to the 2n, the 2nth Bernoulli number. And one thing I did actually forget, I do sincerely apologize. There should just be a pi to the 2k here, and this just stems from the fact that we don't have cotangent of x. It's cotangent of pi x. I do sincerely apologize. So there is a pi to the 2k minus 1 term right here. And I got all the terms. Wonderful. But this right here is just going to be equal to, well, our residues. But our residues are not equal to that's not our final answer actually. It's going to be slightly different because remember we have this negative sign right here. So because of that, all we need to do is take our residue, make it negative. So I'm going to say this is pi to the 2k, just grouping the pi's right here. Pi to the 2k times -1, or n, I do apologize. In my defense, we did say they were equal. But we have pi to the 2n times -1 to the n minus 1, or plus 1, whichever one you like, times 2 to the 2n times the 2nth Bernoulli number divided by 2n factorial. And we said this right here was equal to our sum from k equals -infinity to infinity of 1 over k to the 2n. But that right there isn't actually what we're looking for, is it? What we're looking for is 1/2 of that. So we can just multiply both sides by 1/2 actually. And, well, that right there is our answer. This right here is, rather simply, just gamma, listen to me. This right here is zeta of, must be the factorial on the bottom. This right here is just zeta of any even number. So yeah, I hope you all enjoyed this video. Slightly more zeta stuff for you today. Hopefully I'll do some more stuff like this in the future. And I should really actually do a 100 subscriber special. Thank you all for that, by the way. Anyway, on that note, thank you all for watching, and I'll see you in the next one.